This is the third of 3 lectures from Chapter 9 about chemical bonding, and this lecture will focus on bond polarity. It turns out that there are 2 types of covalent bonds. There is a nonpolar covalent bond, where the electrons are shared perfectly equally, and there is a polar covalent bond, where the electrons are shared unequally. In other words, the 2 electrons in a bond are held closer to the more electronegative atom. So, how you get a polar covalent bond, if you have atoms that are unlike each other, and specifically with significantly different electronegativity, one atom will pull on the bonding electrons more than the other. That creates a kind of partial charge setup, not a full charge like an ionic compound, but the electrons are hovering close to one of the atoms, so there is kind of a partial charge setup. We call this a polar covalent bond, and as a matter of fact, most covalent bonds are polar covalent. Much more common to be polar covalent than non-polar covalent. So it turns out that we kind of presented ionic versus covalent as a real neat, well, it either falls into one box or the other. That's not really the case. Polarity and covalent versus ionic is kind of like a number line, where the polarity increases gradually, and when you reach an ionic bond, that's simply an extremely polar bond. And when you have a nonpolar covalent, it's a completely nonpolar bond. So it's really a continuum, and where we decide to draw the line from covalent and ionic is somewhat arbitrary. I just like this pictorial showing nonpolar versus polar covalent bonds. Now they're both covalent bonds. They both share electrons as opposed to completely transferring them from one atom to the other. But the nonpolar covalent share very nicely, very equally. Polar covalent, one of the 2 atoms wants the bonding electrons much more than the other one, and so it pulls harder. And because of that, because the electrons are actually closer to one of the atoms, it sets up a partial negative charge over the more electronegative atom. The symbol for partial is kind of, it's almost like you're drawing a figure 8 and then you don't completely close it. So again, partial negative is over the more electronegative of the 2 atoms. And then, of course, you need a partial positive over the atom that is less electronegative. So here's an example of a polar covalent bond. Hydrogen fluoride. Fluorine is the most electronegative atom on the periodic table, much more electronegative than hydrogen, so it is going to pull those bonding electrons toward it like crazy. Hydrogen is not very electronegative at all, and so it's going to kind of like, okay, here, I'll let you pull on them harder. And so the partial negative charge ends up over the more electronegative fluorine, and the partial positive charge over the less electronegative. Sometimes you'll see these diagrams, which really have nothing to do with the size of the atoms. It's really a map of electron density, and so the larger the area, the higher the electron density. But we're not going to work a lot with those. I just wanted you to see them. I do want you to be aware that if you are asked, which you will be, to draw the partial positive and partial negative on a polar covalent bond, you can either do what I've shown here, or you can draw what we call a dipole, which is an arrow. You just have to make sure that the tip of the arrow is over the more electronegative atom. I've always remembered that because the back end of the arrow is kind of a plus sign, and that's over the less electronegative atom, or the atom with a partial positive charge. So So to remind you about electronegativity, if you've gotten a little bit rusty, electronegativity increases as we move left to right across a period, also increases as we move up a group. And so a composite line for electronegativity is going a diagonal toward fluorine, where fluorine is the most electronegative atom, and cesium down here is the least electronegative atom. The symbol we use for difference in electronegativity is delta En, change in electronegativity, and it is the change in electronegativity or the difference in electronegativity between two atoms that determines what type of bond it will form, whether the bond is nonpolar covalent, polar covalent, or ionic. All right, so again, just the finish in your primer of electronegativity. Electronegativity is the attraction an atom has for extra electrons. So again, it's always going to be the more electronegative atom that ends up with a partial negative charge. All right, so how do we break down the different types of bonds? If two atoms have very similar electronegativity, we say that they share the bonding electrons equally, and that gives us a nonpolar covalent bond. If the two atoms have significantly different electronegativity, but not hugely different, there will still be sharing, but it'll be unequal sharing, and the result will be a polar covalent bond. If it is a polar covalent bond, we say that there is a dipole. That simply means separation of charge. So it doesn't mean a total positive and negative charge like you have with ionic, but it means some separation of charge, in this case partial. I love this diagram. It's just a pictorial to show the different bond types rather than using a bunch of words. So down here we have electronegativity difference actually. If the electronegativity difference is between 0 and 0.4, that's not very much difference, and so that's where our nonpolar covalent bonds are. If the difference in electronegativity is moderate, specifically between 0.4 and 2, we still call it a covalent bond. The bonding electrons are shared but unequally. One of the atoms is significantly more electronegative than the other, and we have these partial charges or dipole setup and a polar covalent bond. Now, if the electronegativity between the two atoms that are bonding is huge, that is greater than 2, it's a full ionic bond. It just means one of the atoms wants that electron so badly and the other one doesn't care that much, that actually there is an electron transfer and we have an ionic bond. So here are the ranges again for you. If the electronegativity difference between two atoms, this looks like this cut off, is between 0 and 0.4, it is nonpolar covalent. If the difference is between 0.4 and 1.9, it is polar covalent. And if the difference is greater than or equal to 2, that is an ionic compound. So what's a really good example of a nonpolar covalent bond? The diatomic elements. What is the difference in electronegativity between diatomics? 0. You have two of the same thing, so the difference in electronegativity is 0. So these are pure nonpolar covalent bonds. In general, the farther apart two atoms are on the periodic table, the more polar a bond they will make if they bond. Okay? The closer two atoms are on a periodic table, the less polar a bond will be, or the more likely they'll be nonpolar. Okay? That's simply because if two atoms are really far apart, chances are that their electronegativities will also be very different, giving them a more polar bond. All right, so most of the focus on this last lecture is polar covalent bonds. And that's probably, if there's a tricky part to bond polarity, it's understanding polar covalent bonds. There's quite a bit of vocabulary, and then there's symbolism you need to use to describe it. So you may read in a problem, it says something about a dipole moment. The dipole moment is a measure of bond polarity. So something that has a high dipole moment, and mu is the symbol for it, is polar. Okay, something with a low dipole moment is nonpolar. Units for dipole moment are dBi with capital D. You will not see this on my test, but you might see it on the final. Let's just look at some dipole moments, and you'll notice, hopefully, that there's a direct correlation between the difference in electronegativity of two atoms and the dipole moment of the bond. Here's a diatomic chlorine. Difference in electronegativity is 0. Dipole moment is 0. Absolutely no trace of polarity. Chlorine fluoride, they have similar electronegativities. The difference in electronegativity is 1. Not enough to make it ionic, and there are also 2 nonmetals. But it's still not in the range of nonpolar covalent, which, if you remember, nonpolar had a difference in electronegativity between 0 and 0.4. So this is a polar covalent bond, so it does have a measurable dipole moment. I wouldn't call that very large, but it does. Hydrogen fluoride, very polar bond. The difference in electronegativity between hydrogen fluoride is quite high, 1.9. Not quite high enough to be called ionic, which is an electronegativity of 2 or higher, but really close. So, of course, its dipole moment is quite large. And finally, what we know to be an ionic compound, lithium fluoride, it's a metal and a non-metal. Difference in electronegativity of 3, clearly in the ionic range, and has a very high dipole moment. So there is a direct correlation between the difference in electronegativity and the dipole moment. The higher both of these are, the more polar the bond. So to calculate difference in electronegativity, you would be given a table of electronegativities. And just to let you know, fluorine has an electronegativity value of 4. It's the highest electronegativity on the periodic table, so everything else is less than 4. And then I think the lowest electronegativity on this scale is cesium, which is in the lower left corner, and I think that's 0.7. So I think that's roughly the range of electronegativities. But you'd have to be given a table. You would take the difference in the 2 electronegativities to figure out the polarity of the bond. Then you have to remember your ranges. Okay, do you remember where 0.9 falls? That falls within the polar covalent bonding, which I think was greater than 0.4 and less than 2. So once you determine if a bond is polar, then you have to show it's polar by designating either partial charges or showing the dipole arrow. Remember that you put the partial negative charge over the more electronegative atom. Be careful, because it's not always on one side or the other, okay? It's not always on the left, it's not always on the right. So you really have to look and remember your electronegativity trend to know where to put the partial negative charge or where to point your dipole arrow. Here's some practice for you calculating the electronegativity difference in atoms to determine what type of bond. So I showed the electronegativity chart values, I think 3 different times in this PowerPoint, and I've also shown them on the very next slide. You can roll back and forth to see the values. let me go ahead and do the first one for you, and then I would recommend turning off the video and doing the remaining ones yourself. So if you look in the electronegativity table, the electronegativity of hydrogen is 2.1, and the electronegativity of chlorine is 3. Now these electronegativity differences, we're not interested in positive or minus, so just take the absolute difference. So the absolute difference here is 0.9. Now you need to remember your ranges. If it's from 0 to 0.4 is nonpolar. Let's see, greater than 0.4 or less than 2 is polar, and greater than 2 is ionic. All right, so this falls in the polar covalent bond. Anytime you have a polar covalent bond, you must show development of the partial charges. The partial negative goes over the more electronegative atom, which in this case is chlorine, and the partial positive over the other one. You could also draw the dipole arrow instead if you want, making sure that the arrow is next to the more electronegative atom. So using one of these electronegativity tables, again, there's one on the next slide, go ahead and do the remaining ones. It doesn't matter how many of each atom there are, you're just doing it for 2 atoms together. So in this case, you're doing it for 1 carbon and 1 chlorine. The second compound was sodium chloride. Now, hopefully you think, okay, that's ionic. I don't need to subtract those values. I know that's a metal and a nonmetal. It turns out that some compounds we would think would be ionic actually don't have the magnitude of electronegativity difference, so you do need to check. Alrighty, so sodium has an electronegativity of 0.9, and chlorine has an electronegativity, as we just saw, of 3. So the absolute value of this difference in electronegativities is 2.1. So that makes sodium chloride ionic, and so how do we designate that? Well, we have to show full charge for ionics, right? So sodium with a full positive charge, chlorine with a full negative charge. Then we have carbon tetrachloride. Again, don't pay attention to how many of each atom you have. You're just looking at 2 at a time. You're looking at each bond between carbon and chlorine. So carbon has an electronegativity of 2.5. Chlorine, we should know that by now, is 3. So the absolute value of the difference in electronegativities for a carbon-chlorine bond is 0.5, and that's just barely a polar covalent bond, just over the edge of nonpolar. So you would need to show the partial charge, partial negative over chlorine, partial positive over the carbon. And the last bond we had was ammonia, NH3. So we're going to look at the difference in electronegativity between nitrogen and hydrogen. Nitrogen has electronegativity of 3, just like chlorine. And hydrogen has an electronegativity of 2.1. And so the absolute value of those differences in electronegativity is 0.9. Right, smack in the middle of polar. So that is a polar bond. The more electronegative atom would be the nitrogen, and the less electronegative would be the hydrogen. So make sure you're able to do that. You might have asked somewhere along the way, if you're like me, why are we doing this? Who cares? It turns out that bond polarity affects all sorts of properties of a compound as well as its reactivity. And that's because anytime you have any type of separation of charge. So an ionic compound would be a full separation of charge. But even a polar bond that has partial separation of charge still attracts its neighbors and aligns itself in a very particular way. That's pretty strong effect on its properties and reactivity. So just some of the properties that are affected by the polarity of a compound: melting and boiling point, because that's basically the amount of energy it takes to pull those different molecules away from each other. Vapor pressure, how well it dissolves in a solvent, and surface tension. So it actually is important in chemistry. That's it for this third lecture in chapter 9, and that's it for chapter 9.